Hey, good evening, everyone. Welcome to O-level physics lesson. My name is Mr. Chu. Today is the Tuesday, 21st of March. And today we'll be starting on a new topic called the current electricity. Okay, that's our new topic, current of electricity. Okay, so before I go into this topic proper, let me share with you all what did we do with the whole physics. Okay, where are we at? Okay, so we have started static electricity last few weeks. Okay, static electricity is actually a study of charges, okay, that do not move much. Okay, so we are learning about charges. Okay, charges can be positive and it also can be negative. Okay, so we are talking about non-moving charges. Okay, so for the next few weeks, okay, we'll be studying the current of electricity. Okay, so when the electricity actually moves, when when charges actually move, okay, you will bring about this thing called current. Okay, so we have current. So when charges move, you have current. Okay, so before we learn this topic, we talk about charges that do not move. Okay, so this topic onwards, okay, moving onwards, all these topic we'll be talking a lot about current. Okay, that's where charges actually move. Okay, so for practical aspect, these charges that move tends to be the negative charges. In other words, it's called the electrons. Okay, so any question for me now? Everybody okay with the introduction? Okay, we are okay. Give me a yes reaction. Okay, where is my... Yeah, if you're okay with me, with the introduction, give me a yes reaction. Wenxian, I'm still waiting for you to on your camera. Can you please tell me what difficulty are you facing? Okay, so let's look at this. So the last few weeks we talk about, okay, static electricity. Okay, that is where charges that we're talking about the basic of electrical charges. Okay, electrical charges can be positive or negative. Okay, is that clear? Okay, next. Okay, we're going to go through this. Okay, this is a big topic. Okay, so we will take about 2 lessons to just to cover the theory on this topic itself. Okay, so this is the basic of this topic. We're going to talk about current of electricity. And we're going to talk about what is a conventional current, as well as electron flow. We're going to talk about EMF, PD, and then resistance. Okay, so it's a little bit more than the current of electricity. Okay, so we are going to learn all this. Wow. A to O. Okay, A to O. That is 15 points. Okay, so that's what we're going to go through today. Okay, so give me some. Okay, Wenxian. This is nothing to do with privacy. This is about having an online meeting. Okay, where it is for due respect for the participants. Okay, we actually on our camera. Okay, I do not know where you learn this privacy thing from. Okay, I do not appreciate this kind of answer. Okay, right from the first lesson, I already shared with you that cameras are a must. Okay, so I do not want to hear this kind of lesson, this kind of reason from you all. Okay, so I already mentioned to you all before, if you all will have to go to conduct a meeting, you tell people that you want privacy, you don't on your camera. Is that the way you're going to grow up, okay, dealing with this kind of stuff? Okay, Wenxian, do you hear me? Okay, so now I'm waiting for you to on your camera and you're still not being cooperative. So I need to call your mother now. Hey, Wenxian, what are you waiting for? Okay, so Wenxian, I need to have a word with you after this lesson. Okay, I'm very, very disappointed that you're not listening and you're trying to be uncooperative. Okay, so in the previous topic, we talked about charges. Charges can be both positive charge Okay, it can be both positive charge. It can be also be a negative charge. Okay, so a charge can be positive as well as negative itself. Is that clear? Okay, so when these charges all start to move in an organized manner, okay, or in one direction, okay, that is when, okay, a current is formed. Okay, are you able to understand this concept? Okay, so the amount of current, okay, the amount of current, okay, is actually, sorry, the amount of charge, okay, we use this term called charge. Okay, charge is actually measured how many charges are there. Okay, so this charge is the amount of charges there are. Okay, are you all clear about this so far? Okay, so for a lot of things, when we are talking about moving, okay, we move from big to small number, correct or not? Okay, for example, you want to fall down, okay, you fall from level 2 to level 1. Okay, you don't fall from level 1 to level 2. Am I right to say that? Okay, so you only fall, okay, from a big number to a small number. Okay, likewise, for current itself, okay, you actually move from a positive to a negative. Okay, a positive to negative. Okay, so when we talk about conventional current, okay, so if I were to draw a simple circuit like this, we have a plus here and a minus here. Okay, so conventional current tells you that it actually move from a positive to a negative. So in all our calculation, in all our formula, we are all assuming that a positive charge move from a positive point to the negative point. Okay, that is a conventional current. Okay, but we learned in the last chapter, okay, in a substance, proton or the positive charge are fixed in the nucleus of an atom. Okay, it is the free moving electrons that move. Okay, so for a long time, okay, for when people discovered electricity, okay, we all assume that positive charge move from positive to negative. Okay, does it make sense? If I have a positive charge here, down here, positive. So positive and positive will repel. This thing will move to the left, correct? And then when we reach here, okay, positive and negative will attract. So this charge will actually move to the negative point. Okay, so this is what is being assumed, and a lot of formulas, calculation are all based on conventional current. Okay, we are assuming that the positive charge is moving from the plus point to the negative. And then why does it move from plus to negative? Because plus and plus repel, so it move away. And then plus and minus attract, so it moves towards the negative point. Up to here, any question? You have to know any question? Okay, so all our calculation, everything that we do in physics, we are all using conventional current. Okay, in your calculation, in your diagram, when you draw, everything is all about conventional current. Okay, however, okay, we also know that the positive in a metal doesn't move. Okay, the positive charges in a metal conductor, it doesn't move. It's fixed in the nucleus in the atom. Okay, so what is the thing that moves? Okay, so the plus stays there. All the plus stays there. The plus doesn't move. It stays there. Then what is the thing that move? The thing that move are the electrons. Okay, the electrons. Okay, the electron is actually the one moving. So can you see down here? This is a negative charge. The negative charge we call electron. So negative and negative, it will repel. So this electron is the one that moves. Okay, the electron is the one that is moving. Okay, so what I'm drawing here, the blue color, is in reality what is happening. Okay, so the blue color is the electron flow. Are you clear about this? Okay, so the blue color is the electron flow. Okay, whereas the red color, this arrow that we draw, okay, in our diagram, in our working, we will be all using conventional current. Okay, but in reality, it is the electron that is actually moving, okay, in the opposite direction. Okay, but it doesn't spoil the calculation. It doesn't actually disagree with what we're going to learn. Okay, you just need to know that. Okay, in all our calculation, we use the red color drawing, but in reality, it's the electron that's moving in the opposite direction. Okay, up to here, are you all clear about what I'm saying? Okay, if you are clear, give me a yes reaction. If you are not clear, give me a no reaction. Okay, Hao Ming and Wenxian, have your school have your school teach you all this topic yet? Okay, can you give me some feedback in the chat? Have you all learned this? Have you started learning this topic in school? Okay. Wenxian is learning. How about for Hao Ming? Haven't yet. Okay. Okay, so I have actually differentiated the difference between conventional current and electron flow. So basically, everything that we do is based on conventional current. But in reality, that's how the electron actually is flowing. So you don't need to actually deal with electron flow most of the time. Okay, all your calculation, your drawing is all based on conventional current. Okay, clear so far? Okay, next. What is current? Okay, we know what is charge. Okay, we know what is charge. Have we learned charge in a previous chapter? Let's revise. Let me revise what is charge. Okay, so there are different type of charges. Okay, down here did not mention about charges. Okay, so charges itself, okay, the short form is Q. Okay, and charge is measured in coulombs. Okay, coulombs, the unit is the SI unit is capital C. Okay, so what is 1 coulomb? You know what's 1 coulomb? Hold on for a while. Let me Google what is 1 coulomb. Or you can go and Google for me. Can you tell me what is 1 coulomb? Okay, just to let you all know, when we measure charges, okay, so for example, 1 coulomb of charge, okay, is equal to actually 6.24 times 10 to the power 18 electrons. Okay, so that is 1 coulomb of electrons. You have 6.24, then followed by 18.0. That's actually a lot of electrons. So 1 coulomb has so much electron. Okay, so we actually measure charges based on coulomb. Of course, you can say that you can also measure charges by the number of electron and the number of proton. Okay, you can do that, but your number will be very big. Okay, so we actually represent 1 coulomb as this number. Clear so far? Okay, so that is for coulomb. Okay, so what is a current? Okay, we actually talk about charges that move. Okay, so current is how fast it moves. Okay, so let me revise this to you. Current is the rate of, and let me use another color, blue color, flow of charge. Okay, I'm going to explain this to you all. So from here, you can actually come up with the idea what is the current. So current is short form is I. Okay, current is short form is I. Then what is the rate of? When you see the word rate of, okay, just remember that it's always divide by T. Okay, divide by T. Okay, so current is the rate of flow of charge. So flow of charge is the Q. Okay, is how much charges actually flow through that point in 1 second. Okay, so that is the measurement of ampere. Okay, so 1 ampere, the unit is ampere. Ampere is another scientist. Okay, the short form for ampere is capital A. Okay, so this definition I want you to remember because you see this very often. So for example, if I tell you velocity is the rate of change of displacement, can you tell me what's the formula now? Okay, if I tell you this is the definition of velocity, or if I tell you that power is the rate of work done, okay, or the rate of energy used. Okay, then can you tell me what is the formula? Okay, what other formula has the word rate of? So can you see the similarity here? Okay, they all have this thing called rate of and rate of. So I just want you to remember when you see rate of, okay, your formula will all have the divide by T. So velocity is equal something divided by T. Then power is something divided by T. Is that clear? Because you see the word rate of. Okay, then, so what actually is the rate? It's a change of displacement. So your numerator here would be displacement or change of displacement. Whereas for this, the numerator will be things like energy or work done. Is that clear? So do you all see a pattern? Do you all see a pattern that I'm trying to share with you all? Okay, this is the blue color, the one on top here. Can you see this? Okay, so current actually means how many charges flowing through that point in 1 second. Is that clear? So 1 ampere means 1 coulomb of charges, okay, moving past that point in 1 second. Okay, that is the definition of current. Okay, is the rate of the flow of the charges. And what is Q? Okay, what is Q? What is the value of 1Q? Sorry, 1C. Okay, Q of 1C means, okay, 6.24 times 10 to the power 18. Okay, this is a very, very, very big number. Okay, so if your current has 1 ampere, it means there are 6.24 times 10 to the power 18 charges or electron moving through that point. Okay, moving through that point every second. Okay, that's the meaning of ampere. Okay, so far? Okay, so you understand the idea? I'm trying to let you understand the concept, not just memorizing wow, current is a rate of charge. I want you to understand what does this mean. Okay, so up to here, are you okay? Okay, then we all know this formula. I is equal to Q over T. Okay, before I continue, charge is Q, then rate of is divided by T. Understand? Okay, so anything that you see divided by T, you can say that is rate of something. Clear so far? Okay, this formula, if I rearrange, can all of you rearrange and make Q the subject? Okay, make Q the subject. What will be the formula be now? Q is equal to what? So can you type it out in the chat now? Okay, you make Q the subject and tell me what's the formula. Okay, write the full formula, everyone. Okay, very good. For Wenxian, your current is a wrong unit. Sorry, wrong symbol. There should be a capital I. Okay, so your see this capital I. Okay, so you rearrange, you make Q the subject, you get the formula Q equal to capital I then T. Okay, so in my school, when I was a student, my teacher just tell us to memorize Q is it. Okay, Q is it. Is that clear? Okay, any question for me so far? Okay, so let me just continue to I talk about the current. Let me just open a few more things. Okay, so let's draw a simple circuit. Yeah, I don't use resistor. Yeah, I use a bar. Okay. Okay, so the battery powers the electron to move around the circuit. Okay, this circuit is a closed circuit, so the electron can actually flow and complete the circuit. Is that clear? It can actually flow and complete the circuit. Okay, so based on conventional current, it should be moving from positive and to negative. Okay, so just imagine if you're talking about electrons, okay, you're talking about electrons, okay, the electron itself will be moving from the negative and move around this closed circuit. And because the electrons are moving, therefore the bulb will light up. Okay, so far? Okay, so now you know that electrons will move around this circuit. Okay, so how do we measure the current? Okay, what's the definition of current? Okay, current is the rate of flow of electron. Is that correct? Is how much electron flow through a point. So can we just talk about this point here? Okay, so you're actually looking at this point, okay, to see how much charges go through this point every second. Is that clear? How much charges flowing through this point every second? Okay, therefore you got Q divided by T. Okay, and that is your current. Okay, so your current actually measure in 1 second how much charges flowing through this point. Okay, so if you want to measure how many charges flowing through this point, you want to use a instrument to measure this I, the current. Do I put the instrument on the circuit or outside the circuit? So can you tell me? Did I put my instrument on the circuit or outside the circuit? Okay, Wenxuan say on. How about for Hao Ming? Okay, very good. Okay, so you want to measure how much current actually flow through this point. Okay, I'll put the instrument. Okay, I'll put the instrument over here. Okay, so the instrument will be like this. Let me show you. Okay, so I'll put the instrument here, and that's how I'm going to do it. Okay, I will put the instrument here. We call this an ammeter. I'll put it in the circuit so that this instrument can measure how much charges flowing through the point here every second. Okay, so the instrument that we use to measure current, we call this a ammeter. Okay, we call this a ammeter. Is that clear? Any question? Okay, are you clear about this? Okay, so once we know this, let's continue the next part of the lesson. Okay, okay, so what we have done, we have talked about this conventional current. Yeah, this one not nice. Let me change. Okay, we talk about conventional current and electron flow. We talk about current is the rate of flow of charge and we measure in ampere. We have talked about the difference between conventional current and electron flow. Okay, we also rearrange the first formula. We make Q the subject, you'll get this formula. Okay, so basically A and C don't need to go and memorize two different formula. You either understand current is the rate of flow of charge, just understand this and then you can come up with this formula. Or if you want, just memorize the second formula. Q is it. Okay, Q equal to it. Okay, that's how I remember when I was a student. Okay, so for you down here, if you want, you either remember, okay, you either understand that current is the rate of flow of charge, or you just memorize Q is it. Okay, then from these two formula, you can just manipulate, make I and make Q the subject, you can get the other formula. So I do not want you to memorize two formula here. Basically, it's just one formula. Okay, did I make myself clear? Just remember one of these. Okay, if you can, even better, if you understand the first one, okay, you will be able to derive the second one. But if you want to remember, then remember the second one because there's no fraction. Then you rearrange and then derive the first one. Okay, so let me ask you, which one you prefer to remember first? You prefer to remember the first formula or the second formula? Okay, I don't expect you to remember both. So which one do you prefer? The first formula or the second formula? Can you share with me? Do you prefer which one? The first one or the second one? I can't go whatever one. Okay, so we have talked about the current. So next thing we're gonna talk about will be EMF and potential difference. Okay, so for a start, I do not want you all to remember these two things. Okay, so for a start in primary school. Okay, in primary school, we learn the voltage. Okay, we learn this as voltage. Okay, so we talk about this as voltage. Okay, but we come to secondary school. Okay, in sec 4. Okay, we split the voltage itself. Has can be broken up into electromotive force and potential difference. Okay, so this voltage itself can be split into electromotive force and potential difference. Okay, so basically, I just want you to remember these two things to me, they are the same. Okay, they are all voltages. So what is the difference? Okay, the difference is what? Okay, let me just write down here. They are both voltages or voltage. Okay, so what is the difference between these two? Okay, let me write down for you. Okay, the potential difference measure the voltage of a load. A load can be example like a bulb. Okay, anything that actually do work. Okay, that do work. Okay, so that is a load. The EMF is actually the voltage of a source. Okay, source example, things like battery. Okay, cell, and so on. Okay, so to me, these two things are the same thing. They are both voltages. But in secondary school, in Sec 4, you do not use the word voltage anymore. Okay, you actually use electromotive force or potential difference. And don't be mistaken, electromotive force is not a force. Okay, it is not a force. Its unit is not Newton. Okay, it's just a name for the voltage of a source. Okay, now I just want you to understand. Okay, but I don't want you to go and tell people, oh, my teacher say that electromotive force is a voltage of source, but it's a voltage of battery. Okay, don't say that. I'm just saying that to help you all understand and remember better. Is that clear? Okay, so what is the actual definition? Okay, so before I move on, are you all clear that these two are actually the same as voltage that you learn in primary school? Okay, but for the first one is used to measure the source, and the second one is to measure the load. Any question? Okay, if you are clear, give me a yes reaction. If you are not clear, give me a no reaction. Okay, how many are you okay? Okay, so let me explain what is electromotive force and what is PD. Okay, so you see here, this is electromotive force and this is PD. Okay, this is PD. So let's look at the differences. So it's work done. Okay, it is work done by a source. Okay, to drive one unit of charge around the circuit. Okay, it's a work by a source to drive one unit of charge around a circuit. Okay, what is PD? Okay, this is PD. The first one is EMF. So this is called, the short form is the EMF. This one, the short form is called PD. Okay, so what is PD? Okay, can you see down here? Is the work done. Okay, so work done to drive a unit charge through the component. So can you see they are both actually the same thing. They are both work done to drive one unit charge across something. Okay, so basically, are you convinced now? EMF is actually the work done to drive one unit charge. Okay, to drive one unit charge around the circuit. Whereas PD, potential difference, is also the work done to drive one unit of charge past the component. Okay, past the component or past the load. Okay, so basically you can let the component or load be the bulk. Okay, so the PD of the bulk is the amount of work required to drive one unit of charge across the bulk. Is that clear? Whereas for EMF of the battery, it means that it is the amount of work that is able to drive one unit of charge across the whole circuit. Clear so far? Understand? Okay, so can you see they are actually both, to me lah, they are both the same thing. Okay, so what's a unit of work? Can you tell me what's a unit of work? Can you just write down what's a unit of work? Can you remember what's a unit of work? Um, Newton times meter. Okay, what's the short form for that? What's the short form for Newton times meter? Okay, work done. What is the unit for work done? You tell me WD. WD is not the unit. Okay, hello. And I say that you are doing 10 Newton meter of work. Very funny, right? Okay, what do you remember? What's the unit of work done? Okay, the unit of work done is joule. Okay, and what's the unit for charge? Just to revise, what's the unit for charge? Okay, very good. The unit of charge is coulomb. Okay, so basically, the unit of these two things is joule per coulomb. And they actually combine this. Okay, they actually combine this, okay, to give you the unit called voltage. Okay, are you all clear so far? Okay, so sorry, not voltage. They combine this, J over C is the same as volt. Okay, so the unit of electromotive force is joule over coulomb, which is also the same as volt. Okay, 10 volt, 20 volt, and so on. Okay, potential difference is also joule over coulomb. Same thing, it is also volt. Okay, so now you understand the difference between EMF and PD? Okay, let's continue. Let me just explain a bit deeper. Okay, so we have drawn this thing. Okay, so let me just draw another one. Hold on, hold on. Okay, so maybe one of you, okay, never mind, both of you, draw any circuit you all know. Okay, how many you draw here? Wenxian, you draw here. Okay, just draw any circuit that you know, a complete circuit. Okay, very good. Okay, so for example, if I want to find out what, okay, we talk about EMF first. Okay, I use red color. Okay, talk about EMF first. Okay, EMF is actually measuring the amount of work done required to drive 1 unit of charge across the circuit. Okay, so we talk about EMF, we talk about source. Okay, what is the source here? Let me do in red. So can you see? These two are the source. Clear so far? Okay, these two are the source. So how do we measure? Okay, the amount of work. Okay, we don't talk about EMF first. We talk about another one. We talk about PD first. Okay, potential difference is the amount of work or energy that's required to drive 1 coulomb of charge across the load or the component. Okay, so we talk about the load here or the component. Okay, so let me talk about one component here. Okay, how many draw one component here? Then for Wenxian, okay, you draw let's say a resistor here. Okay, so we are going to talk about the potential difference. It's the difference between 2 points. Okay, so can you see? We are going to talk about the difference before and after, let's say this part. Likewise, we are going to measure the difference between the point before and after this resistor. Okay, are you clear about this? Okay, so the potential difference is to measure the differences between the 2 points before and after the load. Okay, so my question now is this. If I want to measure the difference between the two potential, do I put the measuring device on the circuit or outside the circuit? Okay, can you type it out in the chat? Wenxuan say what inside? How many say inside? Wenxuan say outside. Okay, so you want to measure the value between these 2 points. Okay, for example, this battery is a 12-volt battery. Okay, this battery is a 12-volt battery. Okay, so what happened is this battery, when there's no battery, right? This point, this potential is 0 volt. Is that clear? Okay, so if there's no battery, the whole thing is 0 volt. So when you put a battery in here, you are increasing the potential from 0 volt by 12 volt. So if before is 0, okay, if before is 0, okay, this battery itself will increase the potential by 12 volt. Okay, so this point here will be 12 volt. Okay, so what the battery does is to increase the potential by this value of 12 volt. Is that clear? So this 12 volt is your EMF. Clear so far? Okay, let me give you another example. Let's say this one is a 1.5 volt AA battery. Okay, it is 1.5 volt. So at first, this point is 0 volt. Then this battery increased, okay, the potential from 0 volt Okay, it add 1.5 volt to the potential. So after that, this point will be 1.5 volt. Okay, are you clear about this? So if I want to measure the difference, okay, I want to measure the difference between these 2 points. Okay, what I do is I actually take a sensor and I compare the value between these 2 points. Okay, then that is how I measure what is the EMF of this battery. Same thing here. I have a sensor to this point, another sensor to before and after the point. Okay, so this is the instrument that measure what is the difference between these 2 points. Okay, so we call this a voltmeter. Is that clear? So a voltmeter cannot be in the circuit or on the circuit. Okay, because the voltmeter, basically the voltage, we are actually measuring what's the difference between the 2 points. For EMF, it increase the value. Okay, for PD, it decrease the value. Because for PD, energy is used. Okay, for EMF, okay, energy is supplied. Are you clear about this? Okay, are you clear why ammeter is on the circuit? Okay, and then the voltmeter is just measuring the difference. Is that clear? Okay, so this voltmeter is correct. So you want to measure the PD, okay, of this the potential difference between of this resistor. Okay, I want to find out what's the difference between the potential between these two potential. Okay, you actually connect the voltmeter here. Is that clear? Now, for your ammeter to be not disturbing the whole circuit, meaning with an ammeter or without ammeter, your bulb for how many circuit should be as bright. You introduce an ammeter here, it shouldn't affect the brightness of the bulb. Okay, so can you make a guess? What should the ideal resistance of the ammeter? Is it very high or very low? Okay, can you just tell me? The resistance of this ammeter should be very high or very low. Okay, so that you will not affect your circuit itself. Okay, Hao Ming and Wen yes. So ideally, there should be no resistance. So the ammeter is just invisible. It's just there to count how many charges going through that point every second. Okay, so ideally, there should be ideally there should be no resistance, okay, in the ammeter. Okay, now we talk about the voltmeter. Ideally, the voltmeter should have a very high resistance or you have very low resistance. Okay, can you share with me? Okay, so the voltmeter should be very high resistance or very low resistance. All say low. Okay, let's assume if the resistance of this voltmeter is low and you are the current, okay, we talk about conventional current. You move to the bulb, okay, you move through the bulb, you reach this interchange, this dot here, okay. Let me change to spotlight. So you're the current, you're the positive current, you actually move, and then you reach this point. Okay, you reach this point here. Okay, this point. Now, if the voltmeter has a low resistance, whereas this resistor has a high resistance. Where will your current go? Will your current be moving towards the voltmeter or to the resistor? Can you tell me? Okay, so if your voltmeter has a very low resistance, your current will all go to the voltmeter instead. So does it actually change the behavior of your circuit? Does it actually change the behavior of your circuit? You want your voltmeter to be placed here and not affect how your circuit runs. So if your voltmeter has a low resistance, your current actually now go this way. Is that ideal? Okay, is that ideal? So your current end up like this, moving like this. Is this what you want? Okay, so if all your current move to the voltmeter instead, it's no longer working like the original circuit itself. Imagine this is not your resistor. This could be a speaker, it could be a bulb. Okay, and now your current doesn't go through. So it will not work as what you design it to be. Okay, so for this to work what you design to be, you want your current to be moving as per normal, like this. It shouldn't be going to the voltmeter. So to avoid going to the voltmeter, your internal resistance of the voltmeter ideally must be as high as possible. Okay, so your current will not go into the voltmeter. Are you clear about this? Okay, so a voltmeter should have a high resistance, whereas an ammeter should have a very low resistance. Are you clear about this? Are you clear about this? If you are clear, give me a yes reaction. If you are not clear, give me a no reaction. Okay, so what I'm trying to do, what I'm trying to achieve today is to help you understand. Okay, not to memorize but understand. Okay, I hope I achieve that. Okay, let's go back to let's go back to this. Okay, so we have to recap. Okay, we have done this, we have done this, we have done this. We have talked about what's EMF. We also talk about what is PD. Okay, the rest we'll talk about that next week. Okay, we also talk about EMF of a source and the potential difference across a circuit component are measured in volts. Okay, and then I also talk about you're using a voltmeter to measure both the EMF and the PD. Okay, whereas for current, you use an ammeter. Okay, ammeter or a galvanometer. Have you heard of that? Okay, ammeter give you a value. A galvanometer just show you that there is current going through. It doesn't give you a value. Is that clear? Now, we haven't talked about part E. Okay, calculate the total EMF where several sources are arranged in series. Okay, actually quite simple. I have battery 1, battery 2, battery 3. Can? And they all drive one light bulb. Okay, very stupid. Okay, so if there is no battery, the potential will be 0 volt. Okay, the potential should be 0 volt. then the battery itself will increase the volt. Okay, increase the volt here, this value, the volt. Okay, by whatever EMF it produce. So let's say these three battery provide 3 volt of EMF. Okay, so the point after that will be 3 volt. Then if I were to add another voltmeter here, another battery here of 1 volt, this battery will increase the potential by 1. So before it's 3, right? This by 1 become 4 volt. Okay, and let's say this is 2 volt battery. Okay, this 2 volt battery will increase the potential by 2 volt. It becomes 6 volt. Okay, and then how much does the bulb actually use up? Okay, how much voltage does it use up? So before that is 6, after that is 0. Okay, so the bulb actually takes up a PD of 6 volt. Is that clear? So if I want to find the total EMF, all I need to do is to just connect here with a voltmeter with the original point 0. So can you see my voltmeter is supposed to measure the difference between the 2 points. So what's the difference? We have the 6 volt here and the 0 volt here. The difference is 6. So the total EMF is 6. So when you arrange them in series, you just add them together. Okay, 3, you add them together. 3 plus 1, okay, plus 2. Okay, you just add them together, you get a 6 volt. Okay, so when the sources are arranged in series, you just add them together. Is that clear? Are you clear about this? Now, let me give another example. Very stupid example. But what if have you done this before in a school or maybe in your toys? Let me show you what kind of stupid thing you can do. Okay, let me have you ever arranged things like this? A circuit with a bulb. Okay, I arrange like this. Then like this. Then what happened? So this is my minus plus minus plus plus minus plus minus plus minus. Have you ever do stupid thing like this where you actually let me draw boxes so that maybe easier for you to see. I got one battery here, another battery here, another battery here, another battery here, and another battery here. So I got 5 battery. Can you see that? So I did not put them in order. Okay, so when you don't put them in order, you just cancel out each other. Okay, so overall, if I were to put a voltmeter across this point, I say, let's say each battery is 1 volt. 1 volt, 1 volt, 1 volt, 1 volt, 1 volt. Okay, they will not add up to be 5 volt. Okay, because these 4 will cancel out each other. This reading will be just 1 volt. Where this is 1 volt here and this is 0 volt. Okay, are you all clear about this? Okay, so today, how have I helped you all understand this topic? Did I help you understand well, or are you all more confused? Okay, so do you all want me to continue, or should I just end here today? So that next week I will not end too early lah, because the rest of this if I do continue, right, I will end next week very early. Okay, so I will end here today, but you all have any question for me? Okay, if you have no question for me, my 3 checkout question. Number 1, one thing you learned today. Okay, how much you learned today compared to your school? Okay, so give me a rating of 1 to 10. And how well Mr. Chu teach today? Okay, how many has a question? How to use a voltmeter? Okay, that is how much what you learned today. Okay, I thought you asked me asking me a question. How do I use a voltmeter? Okay, how many? Any question for me? So Wenxuan, you have learned this in school, and then half the thing I talked today is new to you lah, or it just help you understand better. Is that correct? All right. If you all have any more question, please ask. If not, how many may leave? Then Wenxuan, you stay back. Okay, thank you everyone. So let me stop my recording. Good night.